Now we're going to go on to quantum experiments. You've seen this distribution probably if you looked at my talk in Huntsville. I gave this. I talk a lot about that you have a probability distribution of all the possibilities. Like we're going to make a measurement. We're going to make a choice. We're going to look in a box and see what's in there. You know, that's making a measurement. Now there's a lot of choices that, I mean, there's a lot of things that could be in there. So let's say, in this case, I've got these letters. I don't know if you can see them very well, but there's all these letters of the alphabet, and there's, 26 of them. And the probability of that letter being in the box is how many letters I have here. So there's more likely there's going to be K's, which is, I don't know if you can see that detail, but these are K's. It's more likely there are going to be K's than there are going to be, P's, because there's only going to be 4 P's in that box. You can think a little piece of paper with a P written on it. There's only going to be 4 of those in that box. And there's going to be all these 25 K's in that box and so on. So we're going to take all these letters and we'll put them in the box. Now if we sum all those up, we get 163. So this Z was a 1 plus 2 for Y plus 2 for X and so on, right? And plus 11 S's, and we add all those up, and the total number is 163 letters. So we got all of those letters written on a little piece of paper in a box, 163 pieces of paper, like this. This then is called the probability distribution of these possibilities, which each letter stands for some possibility, right? So that's the distribution. Now we go into it and we pull one out of the box. We just reach in, we shake it up real good, make sure they're all random, like they do at raffles. We'll reach in and we'll pull out one piece of paper, and that then becomes reality. That's what's in the box. You see, so we're going to make a measurement. We're going to do some kind of thing. We're going to see how something works. And there's various probabilities about how it might work. And we get one of them. And the one we get is a random draw out of the distribution of all the possibilities. So we might draw a Z over here, but it's only one Z in there for all 163. So it's only 1 out of 163 that we're going to pull a Z. You see? But we could get that one, and that would be improbable, but that's the one we'd get. That's how reality is rendered. It's rendered by random draws from probability distributions of the possibilities. Remember we talked about a little earlier that it's so much more efficient to take your deterministic rule set calculations, produce probabilistic descriptions, and then take random draws from those probability distributions instead of having to model everything from the ground up every time you make a measurement. You only have to do it once. You see, for a specific situation, you only have to figure that hard problem out one time. The rest of it are simple draws out of probability distributions. Now that's the way reality works. Okay, now I showed you that before, so I wanted to show it to you again because one, the letters are big enough that you can see, and just to remind you that that's how that's what I mean by a random draw from a probability distribution. That's how we're rendered. Now, so we're going to do a little double slit now, and it'll be a very quick little review. As you see, over here's the particle generator. Now, this is not to scale. I've got these double slits that are like 3 times bigger than the particle generator, right? And the slits are about this big and about that wide. And the particle generator is about this big and about that wide, so don't let that confuse you. But I had to make it so I could get it all on the slide and you could see it. So this is kind of a cartoon, not a scale drawing. All right, so here's a particle generator. And I won't go over this. All of you heard me talk about double slit before, right? Anybody have never heard me talk about double slit? Oh, a few. Okay, then I will maybe do a quickie. The way the double slit works, in this case, we have a particle generator that's going to send out particles. And they're going to send these particles out one at a time. and the particles are going to go through one slit or the other. And I'll explain that to you, because it's like, why one slit or the other? Can't they aim that particle gun? You know, why don't they aim it at the slit they want it to go through? And how come it doesn't hit here in the middle? There's all these questions, you know, that come up practically, and we'll talk about those later. But for right now, trust me, they're going to put out one particle, it'll go through one slit or the other. And I'll show you how that magic is done. Here we have a little wire coming out of this slit to a detector, D2, and one here to a detector, D1. And then these cans are memory. That's storage. That's recorders. R for recorder. Now in this case, I don't know if you see these little green things, but they say on. And the recorders are turned on and the detectors are turned on. So every time a particle goes through one of these slits, the detector will detect it and say, particle just went through here, and that will be recorded. And the time will be recorded. Not only that there was a particle, but the time that that particle was there will be recorded. And what happens is that that particle, once it's recorded, will, as you expect a particle to do, it will go right through and end up over here someplace on this line. And the other one, if it goes through this slit, will end up on that line someplace. Okay. Now, that's what everybody thinks particles should do, and that's really what particles should do. In quantum mechanics, we have this terminology that says that we know that this particle really isn't a particle, it's a probability distribution. And I guess I'll tell you why later on the next slide, for those that haven't been through this before. And we say that that probability distribution collapses the wave. It's a probability wave. The probability wave collapses to a physical particle when the measurement's made. That's the way physicists described this in 1920-something and 1930-something when this was first being done, and Schrodinger came up with the wave equation and so on. So that's what we get. So these now are probability distributions. This is called a single value probability distribution, which means it can only have one answer. It's zero everywhere except right there at that x value. And of course that x value would be right here for that one. That'd be this x1. And this x value will be, this is another separate probability distribution for this one, and right there at that peak would be where the x2 is. So that means the particle, if it goes through this slit, then if it goes through this slit, it's going to have to land here at this x2. That's the only zero probability to go anywhere else. All right, so that's the way that one works. Let's go to the next one. It's just a quick run through. Now here, we're going to look at a case where these detectors are all turned off. Detectors are off. And if the detectors are off, it really doesn't matter whether the recorders are on or off, because there's no detection, right? So the recorders aren't going to get anything. So the detectors are off. Now we can't tell where the particle is. The first measurement occurs here at the screen. There is no measurement at the slits. Now, because this is where they decided that particles weren't particles, they had to be probability distributions, because what happens is that though they originally expected to get the same pattern we looked at before, the two bars, they ended up with this sort of pattern. The photon would come through here and somehow then distribute itself like this, and all these little dots, I don't know, they probably just look like a smear to you, but they're actually made up of a whole bunch of little individual dots. Each one of those dots is where one of these particles landed. So they ran this experiment. They shot individual particles here thousands and thousands of times, and this is the way they displayed themselves on the screen. The dots fell in these, and they didn't like full up or do one stripe and then the next stripe. They just randomly went from here to there to wherever they just hit, wherever they came in. It was a random process, but after you had 1,000 of them, you began to see these stripes appear. Okay? And it was like, what's going on with that? Why do they do that? Why is it when we don't measure what slit they go through, the particles distribute themselves in this very strange way instead of making the two lines behind the slit? Okay, that's when the solution was introduced by Schrodinger of a wave equation. And it's a probability wave. It's not a real wave. Again, it's one of these things that eventually physicists kind of think these waves are real waves. They're not real waves, they're just, it's mathematics to compute a solution, you see. So they decided that the only way to compute the right answer is to say that these were probable particles, potential particles. The particles existed as probability distributions, and because the particle had an equal probability of going through either slit, right? That's when we said it had to go through one or the other. Well, there's an equal probability that it would go through one or the other. Then the probability is this probability, so it would go through both slits too. There's a certain probability that it would go through both slits. Well, probability, unlike particles, can go through two slits at once. It's just numbers in a computer. And then the probabilities have to get summed together. Because here we are at the screen where the first measurement's made, okay? And what we look, when we look back and we see those two slits up there, and I'm the screen and up there are the slits, and I say, okay, I could get probability that they might go through either, so I'm going to get some probability to go through both. It would just be random of me to say, well, let's pick this one. Not my choice, right? I can't just pick one. That means I'm forced to combine them into a single result. Otherwise, it would be just an arbitrary choice by the person making the measurement, and that's not how reality works. Reality doesn't wait for us to tell it what to do. It's got to come to a choice. So we have two streams of probability, and we have to make one answer out of those two. Well, the way we did this is the same way we did with water waves and other sorts of waves, is that here's the wave. It's like a little sine wave. That's not really a sine wave, but it's sort of like one. It's the kind of sine wave you make in PowerPoint tools, easily. It's a PowerPoint sine wave. And anyhow, here's a wavelength. It goes from the beginning here to where it begins again, right? So the wave is up, down, and starts to repeat itself here. So that's one wavelength, and I've got that marked here as one wavelength. Well, notice between these slits, you have distance 1 and you have distance 2, and distance 2 is longer than distance 1. Now, if the difference between those distances, okay, which would be distance 2 minus distance 1, right? That's going to be the difference between them. If that difference is some integer number of wavelengths, then what happens is you get this sort of thing, right? You got two waves, but they're exactly a wavelength separated. Then the peaks will go together, the dips will go together, and it'll look like this. Okay, that's this case. See the red wave and the white wave, they're just a whole wavelength apart, or two whole wavelengths apart, or 20 whole wavelengths apart. Doesn't matter. Some integer number of wavelengths, they will overlap each other perfectly. Now, if they happen to be a half wavelength apart, then you get this case. You end up with this down here, where the two waves are now, we say, out of phase. When one's at his max, the other's at the min. And they do this sort of thing. Okay? Now, these get added together. So when we have this odd integer half wavelength, don't be confused by that. It's like one half wavelength or 3 half wavelengths. We skip 2 because 2 half wavelengths is back to 1 wavelength, which means they go together, right? So it's the odd integer of half wavelengths. Every time that happens, the two cancel out. You get nothing. And this happens with water waves. You know, if this were a big tank of water and I made waves and they came up here, this is the pattern you get on the other side. Okay? So what happens is this point, that's the biggest point because this distance from there to here and the distance from here to here is the same because that's right in the middle between them, you see. So you're always going to get light here. And then you're going to get this darkness when there's 1/2 wavelength difference. They interfere. And then we'll move up. There's a whole wavelength difference. They're back in phase again. We get another point of light. And then there's 3/2 wavelength difference. You get them interfering. It's dark, and so on. Okay, so that's the way waves work. So, because that was kind of the pattern we got, Schrodinger is a smart fellow. He said, well, these seems to be working like, you know, it's the same math. Same math tools will predict the answer. And why does that make sense? Well, because if you turn that light up, if you turn that laser up to where it's making 1 billion particles at once, simultaneously, then you get a light wave, like a flashlight, like this laser pointer, right? And when that happens, we get this diffraction pattern. Always have. That's just regular optics. Well, if when you do 1 billion particles at once, you get this pattern, it'd be kind of inconsistent to say, well, if you did them one at a time, you'd get something else, because all those billion are going through there individually. It's not like they're friends with each other and they're making up this idea that they're going to land over here in a pattern. They're just individual little photons going through a slit. They just happen to be going through with a lot of other little photons. So we can't have this pattern for when the light's turned up high like a flashlight, and a different pattern when it's not, when it's one at a time. So in order for the rule set to be consistent, this is the way it had to turn out. So we end up with probability waves. See? So that's why we have these probability waves. So what the physicists say is that when you have the which way information, which is which slit did it go through, which way did it go, then that collapses the wave, the probability wave, into a particle. And once you're a particle, you have to act like a particle. You go in a straight line, unless acted on by the external forces, and you make these two stripes like we saw before. But when you don't have that which way information, probability has two routes. They have to combine, and they have to combine like this because that is consistent with history. All right, so that's just how this double slit works. And that, of course, started the whole concept of quantum mechanics, is that particles really weren't particles, because real particles can't do this. A real particle, one at a time, has to go through one slit or the other. And you even had physicists in the day saying silly things like, somehow the particle goes through both slits at the same time. Well, not any of the particles that we know of do things like that. It's one or the other. So this is when they first had the idea, particles really aren't what we think they are. They're probability. Or at least that's how we can deal with them. That's what the math says. They act like probability distributions. Okay, so then we'll go on from that. That was just kind of a quick, get us up. Okay. This now is a diffraction pattern, probability distribution. Okay. Now down here, you cannot possibly read this little white line down there because I'm up here and I can't read it. So I know you can't read it. So what these are all just values of x, right? Remember we looked at the screen, and the screen was a y up and an x over, right? That was the way the screen is. Let's see, I'll draw it backwards. Here's the y, here's the x. So these are just the x values along the x-axis. So if you could read that, the first one would say x01, and the next one would say x02, and so on until you get up to here, and it's x45, I think, up here at this other end. So we have all of these little pieces of x. Now I make it into a histogram. In real life, we don't do things with histograms, and we don't take little pieces of paper and put them in boxes to shake them up to draw. That's just illustrative because it makes it simple to understand if we do it that way. Okay, so I'm trying to make this so you get the idea of how it works without necessarily complicating it with having to take an integral of the probability distribution and that sort of thing. So we're just going to look at histograms and keep it simple. So if this is the x-axis, and this is probability. So what it says is that in this case, I have a probability here of 0, okay, of getting into that x position. Then 2, then 3, then I'm reading these little numbers up here, 9, 11, 11, and so on. This one is 20, I think. This is 52, 33, that sort of thing. So each x position has a probability. Well, where would this come from? How would you make this probability distribution? Well, remember, this is a virtual reality. It's a virtual laser. It's a virtual set of slits. It's a virtual screen, right? It's an avatar. It's a virtual scientist's avatar, that's doing it. It's all virtual. So for there to be a laser at all, the system had to produce that virtually. Otherwise, it wouldn't be one. Everything is virtual. So the laser's already been built virtually, at least the logic of the laser, how the laser functions, what you get as the output for what you put in the input. So it's all there. So the way that you make this distribution is you set up that experiment we just looked at, that double slit experiment with the detectors off, okay, so no detection, and then you run it. And the, what shall we call it, I keep calling it the computer, or the larger conscious system, or also there's another one that Ted came up with, the virtual reality rendering engine. Okay, that's kind of for the graphics guys. They use rendering engines to make graphics. So it's a virtual reality rendering engine, whatever we want to call that. It's got this set up, virtual space, because it's a virtual reality. It wouldn't be there if it wasn't calculated. Well, what it does, it just runs the experiment. It just sends one at a time particles through there. And in this case, it sent 1,608 of them through there, and these are all the places where that fell. In the real world, that would be a pretty poor, low-res experiment. In the real world, they'd send 100,000 of them, or 200,000 of them through there, and then instead of getting this blocky histogram, they get a nice, smooth, well-defined curve. Because then instead of breaking it into these 45 bars, you could break it into, 10,000 little bars coming up here that are much narrower. Take each one of these bars and divide it into, 100. If every bar was really 100 little bars, then you'd have 100 times that, which would be, 2 more zeros, 168,800 runs to do that. And then every one of these bars would have 100 smaller ones in it. So now you get real fine definition instead of having this little red curve kind of run sort of through these bars. You could define it real well. So this virtual reality rendering engine just does the experiment, makes this probability distribution. Now that represents this hardware as it stands. Okay, now if you change the wavelength, you have to do it again, see? Because remember that little thing we said that it was the two distances? Well, those distances had to be a fraction or a whole wavelength apart, and that'll change. If you got a different wavelength, all those distances change, so where all those little dots end up changes. Other things you could change the width of the slit. If you made that a little different, well, the difference between those two distances has to do with how big that slit is. Remember, there was one distance went from the top slit up, from the bottom slit up. Well, if you move those slits further apart, now the distances, the difference between those two distances is going to change, so the dot's got to go somewhere else. So this just represents that particular configuration. But also remember, if you've read the book, you should remember that the virtual reality rendering engine, the computer, has billions, probably billions of cycles in between every one of our delta t's. So it's got a lot of time to do all the calculations it needs to do between our delta t's. Okay. It's much faster than we are. Okay. So that's one thing to keep in mind. And the other thing is, because this is a virtual world, it's not like it has to go make a model of a laser in a double slit experiment. It's already done that. The first, when an experimenter sets up an experiment, if that experiment starts with a bent paper clip, well, that's a virtual bent paper clip, and that's, has to be rendered. And then he adds something to that, and they add something to that, and then they put two double slits up, and then they move them away, and they put the slits at a certain thing. All of that's virtual. It's all being done. So the logic for running this experiment to generate this distribution is already in place by the time the experiment's set up, because setting up the experiment creates that logic in the in the rendering engine. So then all it has to do is run a couple of 100,000 through. It's got a distribution. They change a knob or do something or move the slits, calculate it again. Not a problem. Okay, so this is what a diffraction pattern looks like in terms of probability. And you can see I just did some examples that, you know, if you take like what I did here, x32 is 26. x32 is somewhere around here. I think that's maybe the one in the middle. No, it's the one that's 26. Well, I won't try to guess at it. I can't tell. Yeah. Anyway, I can't see them from up here very well. But anyway, if you take this one, let's say any of these, like this one is 52. If you take 52 and divide it by 1,608, that's the probability of getting it in that X position. Okay? So this is really probability times that 1608. If it were real, you know, probability needs to be between 0 and 1. So you take the total of all the samples that you have, in this case all the number of pieces of paper in the box, and divide each one of those by that, okay, then it's between 0 and 1. That gives you a real probability. So this is a 52 over 1,608, and so are all the rest of these. So anyway, that's what that distribution looks like. Now, this is just the X. And say, well, it also has to have a Y position, doesn't it? This is how you get the X position. The Y position has this kind of a distribution. It's a constant distribution. Why is that? Because the two slits were separated apart, right? That makes in X, that's separated along the X-axis, that makes a difference now between which X value. Well, the up and down doesn't make any difference. It's the same probability of hitting high or low in that slit. It's all the same. So basically, the way you can think of this constant probability, you know, here we would say, well, let's say each one of these things had 10 counts in it. So then you add the 10 at this Y distance, the 10 of that, the 10 of that, the 10 of that, for every one of those, and you'd add all those together. What's the probability of picking out any particular one of those? Exactly the same, right? Because they all have exactly 10 pieces of paper with that X value or that Y value on it. So it's random. So when you have a constant probability distribution like this, you end up with a random draw from it. So the Y value is a random draw. All right, let's go on. These will show you a couple other distributions that you might find interesting. This would be a binary. So it's 0, here's the probability. It's 0 everywhere except right at that value and at that value. Okay? So what would you do here if you had n of these at n x18s, and if you had n x28s, well, and you divide it by the total, which is 2n, then every probability is 0.5, right? So that's out of this distribution, a random draw has an equal chance of being at either X position. Over here's the one we looked at first. This is a single value at 0 everywhere except that single value. So if there's n of them, you put n of them in there and divide by n, you get 1. You know, there's a probability of 1 that when you draw from this distribution that you're going to get this X value, and a probability of 0 that you'll get any other one. It just picks a single value. So that's this kind of a probability distribution. So we're going to see these later on, so I just wanted to introduce those to you. Okay, let's go on. Now I'm going to try to explain to you how we clever physicists can make that particle have to go through one slit or the other, and why it doesn't matter how you have that laser gun, you know, whether you're not aiming that particle at anything, and why it only goes through one slit or the other and never hits in between them. Here's how they do that. It's not all that clever. They basically, this is just the front end, just the cap end of that laser gun. Okay, the laser's back behind there, and they're going to turn the laser up. Okay, turn it up to where it's more like a flashlight. Billions of particles coming. And when they do that, they constrain those particles to just coming out of this rectangular shape, because otherwise they hit the inside of that can and they don't get out. Okay. Now, how do you do that? Because laser beams tend to be like this one. You know, they make little spots. Well, you have to take that spot, you have to spread it out, and here I can show you that. You take you have you have a lens. Let's do a double concave lens. And over here, we'll have a double convex lens. And you have a beam coming in here, and it's just this big. Well, it hits this lens, and it does this, it comes this, it does this. It comes up, whoops, I didn't do that very well. I missed my lens. Let's make this lens a little bigger. It hits this lens, and then it goes out straight. And it does just the same thing here. It goes this way to hits, then it goes more, which then hits this lens, and it comes out and goes straight. I'm not a very good artist there, but anyway, so you see you take a little beam here, and you make a really big beam here. So you do that in this thing now, think of it as a circle. Okay, this has got a circular cross section. So it's like a bowl, right? Like a bowl, scooped on either side. So you take two bowls and put their bottoms together, and you got something like this. So it'll take that round beam that comes out of here and turn it into a big round beam that's bigger than that rectangle. So then that whole rectangle is just filled with laser light. And because of that rectangle, then the things that would hit it up in here just don't come out, right? So the only thing comes out is that. Well, you arrange that. You arrange these lenses. You arrange, how far away this is, and there's a lot of little parameters like that. But what you do is you make sure that all of this light that comes through here is inside. I don't know if you can see it. It's a little red dotted line here. So you make sure that everything inside that red dotted light is illuminated uniformly, evenly. Well, what you've just done is you've made it equally probable for a photon to hit anywhere inside that dotted line. Okay, and it's this kind of uniform probability. So yeah, it dribbles off here on the edges some and off here, but basically it goes up here at our x1 and our x2, and it's a flat probability distribution of the illumination of that line inside the dotted red line. So that's the key. That's the secret of aiming the laser gun. Okay, so the P sub box here is just a probability that a generated particle will strike inside the dashed red line. And that's going to be a constant. And later we're going to just let that constant be 0.8, because there's another 0.2 that kind of dribbles out here around these edges. So it's just about, so it's going to be about 0.8, that if you get a particle out of here, it's going to hit inside that box. 20% of the time, it'll miss the box. It'll go outside, and we'll lose those. All right, so next. All right, here's it again. And we're going to say that this is one where they have the detectors on. It's a which-way data. Basically, I just wanted to point out that the Y value here is what we said before. It doesn't matter, you see now, about in the Y direction. It's all uniformly illuminated up and down the Y. So the Y value really doesn't matter. The X value matters because these two slits are separated in X. So if you have a particle that gets detected and has to go in a straight line, it's going to hit either here or here. It's not going to hit over here or up there or anyplace else. The X value are different because you have two different X values for each slit. The Y values are all the same. It's random where it goes from top to bottom. That's why we get these lines like that. And it's a uniform probability distribution in Y. Okay, so we'll go next slide after that. Now, this will get more interesting here. We're going to talk about a little bit about the particle generator. This particle generator, how does it work? Well, if we've been talking about photons, but it could just as easily be, electrons or buckyballs or anything else. But whatever the process is, it's guaranteed that it's basically a random process. You don't create particles this small by manufacturing each one and putting it in a groove with a spring behind it so you can shoot one out at a time. It's a random process when you're dealing with things small. So if you're boiling off electrons, you have a thing called a filament. You run a current through it. The current makes it hot. As it gets hot, it, quote unquote, boils off electrons. It's another one of those metaphors that actually doesn't have anything to do with reality. But it boils off electrons, and then those electrons will be accelerated forward, let's say, away from it by a positive charge, which then attracts it, and the positive charge may be a circle or it may be a grid, but anyway, it gets them moving, and then they move on that. But it's a random process. Nobody knows exactly when an electron will boil off and what direction it'll have or whatever. So it's random what comes out of there. And if it's a laser, it's the same thing. The way lasers work is that you have a gas, and I don't know if you remember I don't know what it was, probably elementary school physics. I don't know if they do this in 5th or 6th grade, or maybe got it in high school. But you have atoms, and they talk about an atom as this nucleus here. There's the nucleus. And then in the old days, they had a shell model of an atom. And here are the orbits of electrons around it. So here's this little electron zips around out here on the outside. And there's other shells up here. And each one of these shells is really a metaphor for a different state of this atom. So if you have an electron here, and then you put some energy in, the electron can jump up to here. Okay? Energy comes in, and we'll move that electron up to the next level. Now, the reason this is quantum is because you can't move one up in between the levels. It's either here or it's there. It's the next one up above that, but it's never, ever in between them. There's only discrete levels that it goes to. All right, so when energy comes in, you can move it up. And if there's an electron up here and it goes back down, energy gets emitted. Okay, so that's just kind of baby physics for how atoms can get excited, pumped up, and how they fall back down and can emit. Well, what happens in a laser is you have this gas full of these atoms like this, and they energize it, put energy into it. They call it pumping. They pump the laser by putting energy into it, and what they're doing is they're moving all the electrons up to a higher orbit. So they just keep pumping and pumping until all the atoms in this gas have their electrons up in a higher orbit, and it all goes, say, from here to here. And when they have that all done and it's all pumped up, then they trigger them to all release. So they trigger them and they all fall back down, and out goes the energy all at one time. That's why laser light is coherent, because they all move out at the same time, so they're all at the same, their waves are all together as they leave. A normal process that you didn't trigger, these things would all just happen randomly. Okay? But the random process here isn't so much the trigger, it's the getting the things to pump up, and which one of these atoms decays when is totally random. How you pump them up, which atoms pump, which don't, it's all random. We have random processes. So the point is, what you're going to get out of a particle generator, be it electrons or buckyballs or anything else, because you're dealing with very small particles, it's going to be a random process that produces those particles. Okay, now let's look at this little picture. Well, there's two pictures here that are important. One is this one. This is a probability distribution for delta t, which is the time difference between successive particles that come out. Okay, so one comes out, and maybe a millisecond later another comes out, and maybe 3 milliseconds later another one comes out, because it's a random process. You can't guarantee exactly when these particles come out. They come out whenever they do. That's uncontrollable. So particles aren't like, things in a pinball machine. You can't just make them come out precisely the way you want, because there's random processes involved. Okay, so that's what it would look like. So this is the delta t, the time between consecutive particles, and there's the probability. So that's delta t, and the PG is particle generator. Also, you've got another probability distribution, and that's the probability of the velocity with which they come out. Okay, that's going to vary too. That's also a random process, because it depends on how they, well, now if that's light, that's a flat line. If it's light, they all come out at the speed of light. If it's electrons or any other particle that has mass, mass as it moves, then there's going to be this probability around velocity too. Now they'll all come out near this, but some will be a little faster, some will be a little slower. They'll all come out near some kind of average time here, but some will be a little longer, some will be a little less. Okay, so that's really what I wanted you to see, those two probability distributions. They're going to make a difference. You see where we're going? This probability distribution, and these are all you need to run a double slit experiment if you are the virtual reality rendering engine. That's all you need. All the rest of it is superfluous. You just need 3 distributions. Okay, we'll go to the next one. Okay, now here is that. I made this a little bigger so you could see it better than that little one. Here it is, and these are in milliseconds down here. So you see it's 5.55 milliseconds at this end, and then it goes up to like 11.11 milliseconds. There's 10 of those, and 20 of the next 2, and so on. And then here's 90 is the big one, and now notice it's perfectly symmetric. There's just the same on the high side as on the low side. All right? Well, that's probably true because most of these random processes are probably Gaussian, and you're going to get symmetric distributions out of them. But anyway, it could be anything. It doesn't have to be symmetric. I just do that because it's a little easier for us to look at, and then I can convince you immediately that this is the average in the middle because it's the same on either side. So we're making it simple. So how does it get these? The same way it got that distribution for the probability of hitting the screen that we looked at. What it does is it has this laser. The scientist builds the laser, right? He puts the gas in the tube, gets the things that excite it, the trigger. He builds all, and as he builds it, that's all being done in virtual reality because this is a virtual reality. So in the virtual reality system, all it has to do is run that at the parameters the scientist sets, and it'll produce, it can run 100,000 particles out of that generator, and it can generate this probability distribution, creates it. All right, now in this particular probability distribution, I'm putting numbers. You say, let's make up some convenient numbers because I know people don't like letters to stand for things and that sort of thing. It's very confusing because it's abstract and our brains aren't used to thinking in terms of abstractions, and that makes it hard. So we're just going to put some numbers in here because then that'll make it sound not so scary. So we're going to say that this is the average, and this average is about 33.333 milliseconds between particles, right? That's the delta t, time between particles. So on average, we're going to have a little over 33 milliseconds between particles. Okay, now what that means, if you have seconds per particle, if you turn that upside down, you get particles per second. So 1 over the frequency is particles per second, equals the period, which is the seconds per particle. See, so that's what we've done here. So if that's 33.33 milliseconds, you divide that into 1, invert it, okay? You get 30 particles per second is what's coming out of that generator. And that's the average value. Really, some of them are going to be as low as on this end, where you have a smaller time between them. That means there's more of them are coming out, right? Smaller time between them, they're coming out faster. Well, on this end, if you do 1 over that, you get like 180 particles per second. On this end, if you do 1 over that, they're coming out a lot slower. You get 16 particles per second. So really, this generator is going to be sending out particles somewhere between 16 and 180 particles per second. Now, that's really not too fast when you get to doing these kinds of experiments. That's really got a long time between things. These experiments measure down in the nanoseconds, and we're only talking milliseconds here. So that's a pretty big space between things. We can time that very easily, even if it seems fast to us. So that's how that works. And this distribution, of course, works the same way. You want to know how long it's going to be before the next particle comes out? You reach into this distribution with a random draw, out comes a number. And say, oh, it's going to be, 22 milliseconds for the next particle. I wonder how long it's going to be with the next one. Take another random draw. Now it's going to be, a different number, 5, or it's going to be 61 milliseconds. So it can pick any of those, and every time a particle comes out, you have to know when, because when is important here in this experiment. So a random draw is made, and that's how long you have to wait before the next particle comes out. So that's this distribution. And up here, what we've done, if we said, kind of waved our hands at this, we said, well, there's the dotted red line. All the light's going to be inside there. And here's our 2 slits. And I kind of eyeballed that, and I said, well, there's about 1, 2, 3, 4, 5. You can put 3 more between these 2. Right, doesn't look about right. You can put about 3 of those slit sizes between those 2. And then there's one that's kind of marginal that'll make up the difference between the, around the edges here. So what I said then is that each one of these is about 1/6 of the area inside the dotted line. Each slit's about 1/6 the area. All right, well, if we're going to have 30 particles per second coming through, and that takes up 1/6 the area, you see, we're going to not get all of them through. Some of them are going to hit between. See, they do hit between. They don't just go through the slits. Some of them are going to go out here and go astray and whatever. But remember, we also said we're going to say that probability that the particle even gets inside the red box is 0.8. So we have 30 particles per second being generated. 1/6 of them could go through either one of these. So if it go through either one would be 1/3, right? So, and that's an 80%. So what that tells us then, if you do the math, is that we're going to have about 8 particles per second, right? 8 particles per second are going to be going through one slit or the other, and about 4 particles per second are going to be coming out of each slit. So that's how we know that we're going to get a particle through a slit every time. You see, it's not that we really have a gun firing a single particle at a slit, and somehow we just don't know where the gun's aimed, so it has probability going through either slit. It's that we're covering the slits with radiation, and the probability, we take away the particles that are going to hit in the middle, we take away the particles that are going to go wide, and what's left is what's going to go through the slits, and we can divide that by 2, and you get about 8 particles going through both, or 4 going through each. So that's just numbers to get you how that works. So that's that's kind of the deal of how the thing works. All right, we can go on through that. Now, if 8 particles go through the slits, then the time between particles is going to be about 1/8, right? Okay. Anyway, so now here's a double slit experiment. And now this is back to the one where we have our detectors, and our detectors are on. When the detectors are on, you see, we can now do this with 3 random draws. So what happens is we're going to start our experiment. The rendering engine has to take a draw from here and a draw from here. That's 1 or 2. From this one is that, and this one is that. Takes those 2 draws, and that'll tell them when the particle arrives. It'll tell them when it arrives, because remember, this detector keeps track of which slit did it go through and what time did it go through it. And the reason it has to keep track of the time is because this over here also has to keep track of the time, and that's how they can tell which point here went through which slit. They look at the times. They say, okay, this time, was 12 o'clock noon, and that one was 12 o'clock noon. Oh, they belong together. Whereas the next one came later. It didn't come until 1 o'clock. Well, those are kind of big times, but even though these are milliseconds between them, that's plenty of time for these measurements to sort out which of these spots went with which of these detections. They're matched up in time. So random draw from here, random draw from here, and then a random draw from here, from whichever. So let's say we get a measurement here at a time here. Well, that tells us that we're going to get something here because we've got it detected. That detector will tell us it's going to have to go through this slit, and it'll get there at a certain time. And then sure enough, we get a point at that time over here in the slit. And because we detected it here, it has to go here. You have a single value. The only place that it can hit on the screen in the X direction is right there. That's the only one it's got. Okay, so that's how that works. Next slide. Okay, so now we have done, the detectors are off. And there's one point that I didn't tell you about this before, and I should have, and that's that I said that if the detector's off, it doesn't matter about these recorders, right? Well, we can do that the other way around. We can leave the detectors on and just turn the recorders off, and we get this same diffraction pattern. So it doesn't have anything to do with the detection making any difference. The detection mechanism is irrelevant. In other words, these detectors can be on and detecting, but they're not recording anything. So it's not the detection of the particle that's the point. It's that the information exists that says what slit the particle went through. That's the which way information is what's key, not really the detection. So we can leave these detectors on here if we want and turn these off. We get the same result because we won't have any which way data. We won't know. So it's not the detection itself that's to cause anything. It's the recording of that detection is what's important. See, it's all about information. It tells you, this is an information-based reality. It's all about information. So anyway, it's the same sort of thing. As it comes through here, the system to do this experiment for a avatar to do this experiment, for a virtual avatar to do this experiment in virtual reality, it gets modeled by the rendering engine as a random draw from here, here, and one from here. You see? So it's just 3 random draws. So we just looked at that one and you saw how that would work. These particles will be coming out, anywhere from 180 down to 16 particles per second, or from about 5 milliseconds to about 61 milliseconds between them. And there'll be all sorts of randomness that'll come out there. But that will tell us what time it gets here. And this, if it's an actual massy particle like an electron, this has to be added in too, because the electrons can be coming out faster or slower. All right? So it takes these 3 random draws. And this random draw, now I think I have that again, the next slide. Yeah, this random draw is from this, right? This very distribution that I showed you before. So the computer does all this ahead of time and gets these distributions and then runs it by making 3 probability distributions. Now what does that mean? That means instead of the system having to calculate and model a particle generator, now you're modeling down at the atomic level, you're pumping up atoms to make the light when they fall back down from their orbits. You got to model how many billion atoms. You have to model the energy force and which ones go up and which ones go down. Then you have to model them all as they travel, and some of them hit this and some of them hit that. You have to model the electrons being boiled off, metaphor. You have to do all of that. Plus, then you do the slits, all of that modeling, and that's for every particle. Every time this thing fires a shot, you got to go through all of that modeling, years worth of crunching on numbers at the atomic level. Well, now we can do that experiment with 3 random draws. Done. So the system has just saved itself a whole lot of trouble. It's impractical to do a deterministic model at that level of detail. It's too much trouble. Now, it can do it with the rule set, but it's a whole lot faster than we are. It's billions of times faster. So that was the last. I just wanted to show that again. That's the one I already showed you. That's the last one it takes the random draw from. Okay, so then let's go on from that. Within the next month or so, I'm going to put out a video that'll have 6 experiments on it. And these 6 experiments are experiments that have never really been done before that I know of, or maybe they have and I've just never run into them or seen them. I'm outside the academic envelope, so there could be that some of them will have been done, but I think many of them won't. And if you recall in some of my lectures, I talk about the envelope experiment. Somebody will nod about that. And I do that, try to be dramatic and trying to put it on a very simple level. But that's one of these experiments. We're going to do that envelope experiment. I've done a little higher tech version than envelopes, using making it a little more scientific than that sort of thing. But that'll be one of them. But there'll be 6 different experiments, and we will predict what the answers are going to be, what is going to come out, and how it'll be done. And I purposely picked experiments that were easy and cheap to do, because I don't expect anybody to get $1 million worth of grant money to go do research, to see whether my big toe or Tom Campbell know what they're talking about. I suspect this will be done by equipment that's already there in a physics department, probably by graduate students who are interested. But all of the 6 experiments are basically cheap and easy as physics experiments go. But you have to realize physics experiments generally are not cheap and easy. Generally, you spend years putting the experiment together, and hundreds of thousands of dollars and lots of man hours. Teams of 4 and 5 physicists working together for a couple of years doing an experiment. It's not like you set this up on your kitchen table, one night and do it. These things are generally big and expensive. This shouldn't be, because these experiments, double slit experiments, have been done forever, all over the place. A lot of this equipment should be available. So I'm hoping that we'll get some enterprising grad students or professors out there that will run these experiments and see whether or not the predictions are true or not. So they're going to test the nature of reality in some unique ways. We're going to be trying to test the rule set and how are the decisions made on, well, I'll just leave it at that. We won't get into detail. I'll be here all day. We'll just say we're just going to look at the specifics of the rule set and try to eke out some things. And there's things that I don't know. I mean, these experiments have never been done before. I don't know how they're going to come out. I know how I think they should come out. And some of them I'm not sure, because I'm not sure how the rule set will be applied to a specific situation. It could be applied this way or it could be applied that way. Either one. I have some ideas about which one of those it'll be, but it could be either. One of them seems a lot more reasonable to me. But so it's going to be that kind of thing. So that will hopefully be interesting. A little experimental evidence, if you will. But it'll be maybe a month. I've got it about 80% done. I've got about another 20% to do on it. I have most of it written up already. It'll be a while, and then I'll have to figure out a way to do it as a presentation at my computer. So anyway, that's coming. A little falsifiability, I guess.